All right, today we are going to do chapter 12. It's our last regular chapter for the semester. Introduction to Organic and Biochemistry. This really is a quick introduction. But do pay attention, especially to things like hybridization, naming, and drawing structures, because that's the kind of stuff that usually shows up on the exam. Speaking of the exam, it's a week. Right back here next Monday. On Wednesday, we're going to go back to 204, and we will do sample exam number 2. So after today's lecture, I will check to make sure sample exam is up. Just like last time, print 2 copies, do 1, hand it in at the start of class on Wednesday. Just a reminder, quiz, the assessment, and all the tutorials have to be done before we take the exam. Any questions? All right. Let's address the concept of valence. Number of bonds an atom typically forms in its ground state. For oxygen, that's water, we form 2. We have 2 unshared pairs of electrons. Nitrogen, we form 3. Boron also has 3, but remember, it does not have an unshared pair. Big Lewis acid here. Carbon makes 4 bonds. Now, there are exceptions, but typically carbon in the ground state forms 4 bonds. Now, these bonds can be single, double, or triple. Single bond here, carbon-carbon double bond, carbon-carbon triple bond. We will see that each of these represents what we call in organic chemistry a functional group. Functional group, the thing that's important to determine the reactivity is, in this case, the double bond or the triple bond. Doesn't really matter what you have attached in other places. Most of the reactivity is going to focus on the simple double or triple bond. It's a nice concept, makes organic quite doable. All right, so carbon forms 4 bonds, right? It's in the second period, atomic number of 6. The electron configuration. Well, carbon is right here. That means that we have filled the first energy level, so that's 1s2. We have filled the 2s energy level here, and we have 2 electrons in p orbitals. Putting it all together, we have 1s2, 2s2, and 2p2. Now the point of this is to try to reconcile this electron configuration with the fact that we form 4 bonds. If you think about it, to form a bond you need a single unshared electron, right? We would expect 2. We don't, we get 4. The reason we have 4 is that energetically it is lower energy to take this electron and promote it to a p orbital. So we wind up with something like this. This is the process of hybridization. Basically, you look for the lowest energy configuration around the central atom. And in this case, for single unpaired electrons, is the lowest energy configuration. Again, this is sp3 hybridization. Remember that. The simplest carbon compound is methane. We've seen methane before. We could call this carbon tetrahydride, but we don't. Organic has its own form of nomenclature. This is the simplest one. 1 carbon is meth. We will see that in a minute. These are the 4 bonds. Now they're all identical. The geometry here is what's called tetrahedral. This is a tetrahedron. The central atom is raised up off the floor in this pyramid sort of shape. For some reason, this is a shape that they never teach you. But in nature, it is perhaps the most important general shape, tetrahedral. All of these angles are 109.5 degrees. The simplest of the functional groups is simply carbon connected together with hydrogens all the way around. Every carbon has 4 bonds, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. These are all sp3 hybridized. And again, this is a functional group. It's called an alkane. Alkane, A and E denotes it is an alkane. Virtually all alkanes have the same inherent reactivity. In addition to this representation, we could also show this using a ball and stick model. As we do that, we can see the tetrahedral links. Let's go back to that one. This tells you what the molecule is, but doesn't show anything about the geometry. This shows the geometry very nicely. CH3, CH2, CH3. Again, all the bond angles, 109. We can also take the carbon chain and we can add branches to it, called a branch chain. This has 1, 2, 3, 4, 5 carbons. Again, it's an example of a simple alkane. If we put it in 3D, you can see this single CH3 sticking up, 1 on each end, 2 CH2 here, and a CH. Once again, 4 bonds for every carbon. The alkane has a general formula. Cn, where n is an integer, And the number of hydrogens is 2N plus 2. Here we have 3 carbons, so N is 3. We have 8 hydrogens, 2 times 3 plus 2 is 8. Here we have 1, 2, 3, 4, 5 carbons, and we have 12 hydrogens. Once again, Cn H2n plus 2, and that's an alkane. Other functional groups that we just saw, when we have a carbon-carbon double bond, we call that an alkene, E-N-E. This is ethene. It has 2 carbons. This is ethyne. It has 2 carbons but has a triple bond, not the double bond. Again, these are examples of functional groups. Now, I said that the single carbon was called a meth. 2 carbons is called an F. There's an entire set here. Number of carbons and the name. This is the abbreviation, if you will. Methane, ethane, propane, butane, pentane, hexane, heptane, octane, and all the way down to watts. Again, the simple formulas. You probably should know or have a good feel for the names, maybe up to 8. Okay? We don't go much above that, but up to 8, and they're fairly simple. This is called an alkyl group. These are all going to be based on methane, which means they have 1 carbon. Methyl group, we attach something to one of the empty bonds here, and that is just generally known as a methyl CH3. An example, if we put an OH out here, this is methyl alcohol. Put an NH2 here, this is methylamine. Meth, again, tells us the number of carbons in our longest chain. So one more time, meth, 1, F, 2, prop, 3, bute, and pent. Any questions? Now, I did say that you needed to know basic nomenclature, but it's going to be pretty basic on the exam. So you don't need to really worry too much. Carbon compounds can get very complicated very quickly. One of the neat things is that you can take and not just have a branched chain alkane, but carbon can wrap around itself and form rings. This is a 6-member ring, this is hexane. This is a very complex molecule. We have 1, 2, 3 rings in this one particular molecule. One of the great challenges in organic chemistry in the lab is to get a molecule, something like this perhaps, and try to figure out what it is. Okay, that's really tough. Structure determination. We can also stick in heteroatoms. Heteroatoms in organic chemistry mean anything that is a carbon or hydrogen. This is glucose. We've seen this before. The red denotes an oxygen. So these are all OH groups. We have a ring here. There's an oxygen in the ring, actually. This is morphine. Again, morphine is a very complex molecule. We have a ring up top here, we have another ring down here, and another ring bridging. Again, organic compounds can get very complicated very quickly. Representing them. This is the ball and stick that we've been using. This is called a Dryden model. I'm not sure why he got all the credit for it. All it is a ball and stick without the balls, but nonetheless, it's a nice way to do it. This is space filling. Now, space filling tells you what the molecule really looks like. All of these are on the same scale. I just told my computer to change the display. So this is what it really looks like, but you can't tell too much. These are much better at telling you exactly what's bonded to whom. If you want to represent a carbon compound, this is a very nice way to do it, but nobody can draw that, right? This is the molecular formula, C4H10. That tells you the mole ratio, but it tells you nothing at all about the shape or what's connected to whom. This is called a condensed structure. This is very common. If you look at this, we have a CH3, CH2, CH2, CH3, and we just string them together. The assumption is that all of these carbons are bonded together, just like they are here. This is called a Kekulé structure. It's a real pain, it's a real bother, but you show all of the hydrogens, all the bonds, whatever. It's a lot like this, except not artistic. This is what we will use, basically in organic. It's called a line structure. Whenever you see a structure like this, whenever you have a vertex, so right here and here, that's a CH2. Whenever you have a line that heads up and stops, that's a CH3. Now, why is this drawn as a zigzag? Look at the model. That represents the backbone of our carbons. Typically, a nice zigzag. Any questions? If I ask you to draw a structure, I expect you to use some version of a line structure. Now, line structures themselves can also be drawn several different ways. This is a strict, so here's the Kekulé going to the line. Sometimes, to make sure people understand that that's a CH3 up there, they just draw it in. So this pretty clearly says we have a CH3, CH2, CH2, CH3. Purists, however, look at this and argue that this kind of looks like the hydrogens here are bonded to the carbon. So quite often you'll see it reversed, so it's a little bit less unambiguous. You'll see every conceivable version of line structures if you do organic. In organic chemistry, the geometry of the molecule is very important. There are interactions that occur all along the carbon-carbon chain, and one of the things that you do in organic is to try to understand these, explain them, whatever. This is our line drawing with the carbon backwards. If we take that line drawing and we turn it so we are looking straight down this bond here at a slight angle, we could draw what's called a sawhorse projection. In a sawhorse, this is our front carbon, that's the back carbon. We show these guys, and the reason the sawhorse is useful is because it makes it very clear that in this molecule, the two methyl groups are on opposite faces. We could go one step further and do what's called a Newman projection. Again, that's our front carbons and the back. If we take and look straight down this bond, so the front carbon here is this guy. The back carbon we show as a ball, so you could see it. This is called a Newman projection. And once again, it's widely used to show the geometry of the groups in the chain. It's a little short video. This is our writing model. And again, if we take and we turn this so that this carbon is now coming toward us slightly, we get something like this. That's our sawhorse. And then we turn it all the way, we get the Newman. Any questions? Well, let's put some of this to use. Take this structure and convert it into a line drawing. Now, the way to do this, you want to look at your compound and figure out the carbon chain. So in this condensed formula, we have a CH3, so this carbon's bonded here. This carbon has two CH3s on it, two methyl groups. The carbon is then bonded to this, which is bonded to this, which is bonded to that. So we have a total here of 1, 2, 3, 4, 5 carbons in our chain. Again, this one has 2 carbons instead of 2 hydrogens. Okay, so you would start off by drawing a zigzag with 5 carbons. Try it. It's going to look something like this. 1, 2, 3, 4, 5. Now, you look at your carbon chain here and see if you have any branches. Well, we do. We have 2 methyl groups attached to carbon number 2. Carbon number 2 is here. Remember, a methyl group is going to be a truncated line. So we simply draw it like this. That's 1, and that's 2. And that is our line drawing. This guy, we have 6 carbons in a ring. Now, because all of these bond angles are 109, the ring isn't flat. In fact, it does a zigzag just like these, up, down, up, down, up, down, right? So, the most accurate way to represent this is to simply do the up, down, up, down, up, down, and write this as your structure. This is what is known as chair conformation of cyclohexane. Some people look at this and say, oh yeah, it looks like a lawn chair. That's where it came from. If you instead wanted to draw a perfect hexagon like that, you can. Although the zigzag is preferred, to be honest. All right, we look at this guy. It's a Newman projection, isn't it? What we have to do here is to figure out our longest carbon chain. Let's start here in front. This is the front carbon. We have 1, 2, the back carbon is 3, and then 4, 5. Doesn't matter where you start. 1, 2, 3, 4, 5, 6. Yes, that is our longest chain. So we are going to write a zigzag with 6 carbons. Go ahead and do that. And it's going to look something like that. I've labeled carbon 3 and carbon 4. Carbon 3 is the one in front, 4 is the one in back. 3 has a methyl group attached, and so does 4. We simply show those as truncated lines again. And that's our structure. 1, 2, 3, 4, 5, 6 carbons, a methyl group on carbon 3, a methyl group on carbon 4. Now, one of the interesting things about carbon compounds, these are all single bonds, aren't they? A single bond has free rotation, which means you can spin around this axis over and over and over again. In fact, these things spin roughly 1,000,000 times a second. That means that if we drew this compound that we just did in this particular conformation, it is 100% proper to draw it in this conformation as well. Because this is spinning around, so is this, and so is this. These are referred to as conformational isomers. Isomers are molecules that have the same numbers and types of atoms, but they're different. So this guy and this guy are different. They're different energetically, but they're the same molecule. In fact, because the rotation is so fast, they are essentially equivalent. So at room temperature, these two are the same. We can't distinguish them. This is an example. It's a little animation. Not great, but here we have 1, 2, 3, 4, 5 carbons in a chain, and I turned on dynamics. And as you can see, this molecule rearranges itself in space constantly. So any of those conformations you draw are the same. This simply reinforces that. For this guy, this is our longest chain, 5 carbons with a methyl on number 3. Again, 5 carbons, methyl on number 3. 5 carbons, methyl on number 3. Same compound, conformational isomers. So, wow, how are we going to name these things? You know, back in the old days, if you discovered a compound, a new compound, you could name it yourself. You could name it after your dog if you want, all right? But that didn't really work very well because there are billions and billions of organic molecules. So we have to come up with a set of rules. International Union of Pure and Applied Chemistry has rules for branched alkanes. Step 1, we look at our molecule and we find the longest continuous chain of carbon atoms. So look at these two and come up with a chain. If we let this be our main chain, we would have 1, 2, 3, 4, 5 carbons. If we let this be our main chain, we'd have 1, 2, 3, 4, 5, 6. That's our longest chain. Over here, 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. I think that's our longest chain. Once we have identified the longest continuous chain of carbon atoms, we need to come up with a name. We're going to number beginning at the end that is closest to the first substituent on the chain. Now that's a branch, okay? If we started here, if that was carbon 1, our first branch would be carbon 2, carbon 3, carbon 4. If we start here, our first branch is at carbon 2. So 1, 2, 3, 4, 5, 6, 7. This is going to be carbon 1. Also 1, 2, 3, 4, 5, 6, 7. That works too. Let's just take this one and we'll number it this way. This way our first substituent is in carbon 2. All right. Next we have to come up with a name. We are going to name the substituents based on the number of carbons that are attached. We're going to name the main chain based on the number of carbons in that chain. So with this molecule, at carbon 2 we have a single branch. Remember, that's called a methyl group, meth 1. Over here in carbon 4 we have a 1, 2, 3 carbon chain. That's a propyl. And our main chain has 7 carbons. What was 7? That's a hept. This is an alkane, so we end it in A and E to show that the functional group is alkane. Now we're going to arrange these alphabetically using hyphens and commas to separate the numbers. So we'll start off with carbon 2 has a methyl group. Carbon 4 has a propyl group. And our parent is a heptane. And that's the name. Oh, it gets to be fun after a while. Look at this guy. Find the longest chain and decide which carbon is going to be number 1. Doesn't matter where you start here, these are all equivalent. So it's going to be 1, 2, 3, 4, 5, 6, 7, 8, isn't it? This is carbon 2. It has the substituents in it that are closest to the end. Here we have this at carbon 1, we will be in carbon 3. So that's carbon 1, that's carbon 8. So what we have here is a carbon 2 with 2 methyl groups. We're going to use dimethyl to express that. At carbon 4, 2, 3, 4, we have a 2 carbon chain. That's an ethyl. We have a 3rd methyl out here on carbon number 6, and the ethyl group here on carbon 4. Our main chain has 8 carbons. That's an octane. So to put this together for a name, we have 3 methyls, that's a tri. They are on carbon 2, and carbon 6. We have an ethyl group here on carbon 4. Alphabetically, ethyl comes before methyl, so we'll start off with our 4-ethyl. Next, we have 3 methyl groups. 2 are on carbon 2, 1 is on carbon 6. We show that as a 2,2,6 trimethyl. Finally, all of this is attached to a chain of 8, so it's an octane. And that's our name. Any questions? Let's just take that basic structure. And what I did was I took this methyl group and I put a chlorine on it. Okay? So instead of a trimethyl, now we have a dimethyl. And here at carbon 6, we have a chlorosubstituent. So putting it into our name, again, we have 8 carbons. It's an octane. We have an ethyl group at carbon 4, a chlorine at carbon 6. We will start with the chlorine, 2 methyls on carbon 2, ethyl on carbon 4, chlorine and carbon 6. Alphabetically, chlorine comes first, then ethyl, then methyl. Again, it's an octane. 6-chloro, 4-ethyl, 2,2-dimethyl, octane. Now the good news is, on the exam I would never give you this, would I? No. Of course not. Not unless this was organic. Let's look at some that would be eligible for exam questions. This guy. It's a sawhorse configuration. First thing you want to do is find your longest chain. Well, I can do 1, 2, 3, 4, 5 carbons and get a chain. Now, I need to decide which is carbon 1. Here's our side chain. It's a methyl group. That's carbon 1, 2, 3. 1, 2, 3. So it doesn't matter. It's in the middle. We can make either one carbon 1. Because we have 1, 2, 3, 4, 5, we would start by drawing a zigzag, wouldn't we? If we want to come up with a name, we look at this and say, okay, it's a pentane, isn't it? 5 carbons. On the pentane, on carbon number 3, we have a methyl group. 3-methyl pentane. This exact name was on exam number 2, I think, a year ago. So this is the level. 5 carbons, it's a pentane. Carbon number 3, a methyl group. Look at this guy and come up with the longest chain. These little dash bonds and the bold bond here is meant to show the stereochemistry. What this says is that this methyl group is pointing back, this one is coming towards you. Well, looks to me like we could do 1, 2, 3, 4, 1, 2, 3, 4. Yep, that's it. 4 carbons. We want to number, so carbon number 1 is closest to the first substituents, so this guy would be carbon 1. Now, what we have is 4 carbons, that's a butane, right? Attached to the butane at carbon number 2, we have 2 methyl groups. So it's going to be a 2,2-dimethyl butane. Now, the other option for exams is to give a name and say, draw me a structure. Our first one here, it's a butane, 4 carbons, right? It has 3 methyl groups. 2 of them are in carbon 2 and 1 in carbon 3. See how systematic this is? So, I would start by drawing my zigzag with 4 carbons. Do that. 4 carbon zigzag. Up, down, up, down. Something like that. Now we're going to pick one end or the other and make it carbon 1. Doesn't matter which one. On carbon number 2, we're going to put 2 methyl groups. So that's here, 1 up, 1 down. Carbon number 3, we have our 3rd methyl. Carbon number 2, 2,2-dimethyl. Carbon number 3, we have another methyl, making it a trimethyl butane. All right, do this one. It's a hexane, start with a 6 carbon zigzag. And make one end or the other carbon 1. In carbon number 2, we're going to have 2 methyl groups. So that's here. We'll show it as an up and a down. Carbon number 3, we'll have an ethyl group. That's 2 carbons. It's carbon 3, so it'll be an up and over. And the structure looks like this. 2 methyl groups in carbon 2, an ethyl group in carbon 3. Do your last one. It's an octane, so 8 carbons in a zigzag. And choose one end or the other to be carbon 1. Now we're going to have 6 methyl groups on this carbon, or this chain. They are in carbons 2, 3, 4, 5, 6, and 7. Each of those is just a single straight line coming out. And it looks like that. Any questions? Now, once again, we draw these molecules this way, but remember, these chains are twisting and turning and doing everything in sight. That makes them isomers. Again, that's conformational isomers, we said. Again, we cannot separate them, so these are just deemed to be identical. You can imagine how difficult it might be to grade an organic exam, where you have structures, and there's always somebody that wants to draw this way. So you have to be able to figure out what's what. I said that these were energetically different, but again, they rotate so quickly, you can't really tell. This is 2 carbons, so it's ethane. And you can imagine there are 2 distinct structures. One is called eclipse, where everything is lined up against each other. And the other is staggered, where we have a hydrogen up and a hydrogen down. This is ethane as it rotates. And I want to draw your attention to right here, okay? See the little fuzzy stuff that shows up when this rotates to the eclipsed form? That's energy. This is hindering the rotation because they're kind of bumping into each other a little bit. We can show this with an energy plot. And again, as we go around, every time we hit an eclipse conformation, it's about 12 kilojoules or a couple kilocalories difference. That means if we took this thing down to almost absolute zero, the more stable conformation, this guy would freeze out. So we could separate them, but we don't. Any questions? All right, well, we talked about conformational isomers. Another type of isomerism is constitutional isomers. Look at these 2 compounds and come up with the longest chain and a name if you wanted to. This guy has 1, 2, 3, 4, 5 carbons in his longest chain, has a total of 6, 7 carbons to it. It's C7H16, right? This is 1, 2, 3, 4, 5, 6, 7 carbons also. It's also C7H16. This is our longest chain here. Here's our longest chain here. Clearly, they are different molecules, but they have the same formula. These are different chemical compounds, and we could separate these because they're different, called constitutional isomers. Now this brings us to a fun game. Organic chemists like games. Write all the constitutional isomers of C3H8. 3 carbons, 8 hydrogens. See if you can write 1 or 2. Actually, you can only write 1. C3H8 is a straight chain alkane. It's propane. 1, 2, 3. 1, 2, 3, 4, 5, 6, 7, 8 carbons, hydrogens. This one was never on the exam. Make it slightly different. C3H6. See what you can do with that one. There are 2 actually. Now remember, you can put in a double bond if you want. You can also make a ring. There are the two. Yes, this is cyclopropane. It's real. It is real. It's highly strained, but it's real. This has a carbon-carbon double bond. They're both C3H6. To wrap carbons into a triangle, you put in a lot of energy. That energy is still there, right? If you break this open, it kind of goes like this, doing, okay? That means that this is a high energy molecule and it's used as a rocket fuel. C4H8. Now I did put this one on an organic exam once. Remember, we can do rings, we can do double bonds. There are 5 constitutional isomers, and they look something like this. 1, 2, 3, 4 carbons, 1, 2, 3, 4, 1, 2, 3, 4. Here we take our triangle, stick a methyl group on it. And yes, this is cyclobutane. Again, tie it back a bit, not as bad as here, but again, a high energy molecule. Now the one that I always threatened to put on the exam but never did, we just take our C3H6 and we stick in 2 oxygens. Now remember, the oxygen can be a single bond or a double bond. Same thing with all the carbons. This one never quite made it on the exam because this is part of the answer. Here we have carbon-oxygen double bonds. Here we have oxygens in the ring. We have 1, 2, 3, 4, 5, 6 here. And we have these guys as well. Organic molecules can get so complicated even with very simple formulas. And again, in the lab, you can do an analysis and say, well, okay, I know this is C3H6O2. Yeah, well, which one is it? That's the real challenge. Great intellectual challenge. All right. Here I have 2 compounds. Are they identical? Are they different compounds and not isomers at all? Or are they constitutional isomers? Simplest thing to do here is just to come up with your longest chain. We have 1, 2, 3, 4, 5, and 12 hydrogens. Over here we have 1, 2, 3, 4, 5, 6, and 14 hydrogens. They are clearly different chemical compounds, and we can separate these. They are not constitutional isomers, they are just different. Look at these 2. Now in the condensed structure here, this carbon, we have the H afterwards. That means the hydrogen is attached to it. And the chlorine is also attached to it. So, in this one, we have a main chain of 1, 2, 3, 4, 5, 6 carbons. We have 2 chlorines. One of these is in carbon 3. Oh no, I guess it'll 1, 2, carbon 2. Fluorines in 2 and 4. Over here we have 1, 2, 3, 4, 5, 6. 6 carbons. Fluorine in carbon 2. Fluorine in carbon 4. These are the same thing. Any questions? All right. Let's move on to functional groups. We have met the carbon-carbon double bond and triple bond before. This is an alkene, we said. That's the functional group. 2 carbons, so this is ethene. 2 carbons here, this is F. And the functional group here is an alkyne, so this is a YNE, F-ine. Now, when we go to make a double bond, what we're going to do is take orbitals and hybridize them. Again, we're looking for lowest energy. To form our backbone, that is the sigma network bonding the carbons together, we're going to need 3 orbitals because we're going to make 3 bonds. 1 S, 1 P, and another P. We will combine these together and we'll make this structure. Energetically, we want 100 degree, 120 degree angles between everything. Okay? We have 3 bonds on each carbon, 1, 2, 3, so we need 3 orbitals to do that. But remember, every carbon has 4 orbitals, right? So we have a leftover orbital here and here. They are p orbitals, and each of these carbons has a p orbital with an electron in it. So we can show that on this carbon and this carbon this way. So here's our sigma network, sigma bonds, single bonds, and here we have our 2 p orbitals. When the 2 p orbitals line up adjacent to each other, the electrons share. They share between the 2 carbons, and they form something like this. Looks kind of like a hot dog, right? If we look in the middle, there's our sigma network. These are the p orbitals above and below. Since these come from p orbitals, this is called a pi cloud, Greek symbol pi. We show the structure of this as a double bond. One is the sigma bond, the other is the pi bond. Here's our carbon-carbon double bond. Again, one is a real bond, and the other is this thing. Now this pretty much defines the reactivity of an alkene, because if we do an electrostatic potential map, here, right over the 2 carbons, we see we have this huge cloud of electrons above and below. Electrons mean reaction. There's also something interesting about this. In order for these guys to overlap, they have to line up directly, right? So if I took this sigma bond and I simply rotated things like this, I would get this. These are at right angles to each other, and they cannot overlap. So this is very high energy, this is very low energy. Interesting consequence here. Everyone take a look at my little laser pointer, right? How do you see that? It's chemistry. Vision. This is a trans double bond. Trans simply means here's our double bond. Our substituents go up and down. Cis double bond goes up and goes up. These are isomers, but we cannot rotate this one to this one unless we put in energy. So these are separate, distinct compounds. When you look at my red laser pointer, or at anything for that matter, there's a compound in your retina called cis-retinal. We'll do the aldehyde in a bit, but this is what it looks like. Bunch of double bonds, ring, whatever, complex molecule. This is a cis double bond. Okay, they're on the same side. When light hits this guy, it takes this electron in this double bond and excites it. When it excites it, it becomes a single bond and rotates to the trans isomer. That's vision. Every time you see a photon, every time a photon strikes retinal in your retina, we get a sonorization and your brain detects light. Kind of neat. Again, these are isomers. They differ in the way they're arranged. Technically, we call these stereoisomers. All right, well, we built a double bond. Let's build a triple. For a triple bond, we're going to start with a single. So we need two orbitals. This 180-degree bond angle. Each of these carbons has two p orbitals left now. If we put those on, it looks like this. We can line these two up. We can line these two up. This is going to be one pi bond. This is going to be our second. We wind up with two overlapping pi bonds, two hot dogs, if you will, and that's our triple bond. One sigma and two pi's. If we look at the electrostatic potential map, we can see the big belt of electrons here right around our triple bond. So, single bond sp3 hybridization, double bond sp2, triple bond sp. Make sure you know these things. As far as functional groups go, we said this was an alkane, this was an alkene, and this was an alkyne. Anything with a triple bond is an alkyne, double bond is an alkene, only single bonds alkane. Functional groups, again, are very useful because basically all alkenes are going to undergo the same reactions regardless what's attached to it. Other functional groups. This is the alkene we just saw. We put an OH on, we call it an alcohol. Put the oxygen in between the carbons, it's an ether. Again, they have characteristic chemical behavior. Now, what I mean when I say that, if we take an alkene, and I haven't shown anything on it here, because this can really be anything. If we add bromine, Br2, we add the bromine to the double bond, and we wind up with a structure like this. So 1,2-dibromide. The two bromines are always on opposite faces. Another thing that organic chemists do is try to figure out why in the world this happens. Okay, why is this? Pretty simple, really. This is an alkene, a cycloalkene. There's a double bond. That's bromine. If we add bromine to this, remember our double bond here had lots of electrons, right? Those electrons come out, attack the bromine, it splits, and we form an intermediate here. This is called a bromonium ion. The thing about a bromonium ion is that it's big. Bromine is big. Now remember, we also have a Br minus that we kick out. It would love to get in here and react, but this is so big it can't get there unless it comes in from the opposite side. The ring opens and we get our trans dibromide. Organic mechanisms are called, again, a wonderful exercise in logic. This is just an example of functional group reactions. There's actually 2 pages to this. So in organic chemistry, one of the things that makes it difficult is you have an alkene, you know it's going to react with something and make whatever, but you have to know all of these. That's a lot, but it's fun. All right, let's go ahead and look at our functional groups. We've done alkane, alkene, alkyne. If we take 3 double bonds and we put them in a ring, each of these carbons has a p orbital associated with it. Here's our line structure. These are the p orbitals, okay? They all kind of overlap, and we form a structure like this. This is benzene, huge electron cloud in the middle, called an arene as a functional group. Beautiful molecule. We stick a halogen on, we call it a halide. OH is an alcohol. Oxygen in the middle is an ether. An amine. Remember the amino group here, but we'll see it in just a minute. Simply an NH2 attached to the carbon. Carbon-carbon triple, carbon-nitrogen triple bond is a nitrile. This is a nitro group, NO2. Thiol. The thing about thiols is they stink. Literally, they stink. If you know somebody that does organic chemistry and works with thiols or sulfides, you don't come close to them. It will stay on your breath for a year. These are the essence of skunk. Again, they're all thiols. If we take a carbon and double bond it to an oxygen, we get what's called a carbonyl compound. These are differentiated by what's attached out here to one side. So if we have a hydrogen, it's an aldehyde. We have 2 carbons, it's a ketone. If we have an OH, it's a carboxylic acid. This is an ester. Again, remember carboxylic acid. This is an ester where we have another carbon attached instead of a hydrogen. This is an amide if we have an NH2 attached to the carbonyl. And again, that's important. Acid halide, acid anhydride, whatever. Now, carbonyl compounds are perhaps the most important functional group in organic chemistry. That's because the oxygen, being much more electronegative, sucks the electrons up, making this carbon positive and the oxygen negative. The electrostatic potential map shows that. Big red oxygen, big blue bottom down here. Now, why is that important? Because this carbon is positive. Things with electrons react with it. I said that we should remember amines, carboxylic acids, and amides, right? That's because these are the amino acids. An amino acid has at least 3 functional groups. There's the amine, here's the carboxylic acid, and it'll have a side chain. There are 20 different side chains in amino acids. These 3 are positives, these 2 are negative. Here's it. Everything after the amino group is a side chain. These are polar uncharged. So we have an OH, we have another OH, different place. This is an amide, and this is an amide, extra carbon. Special cases, we have a thiol. You could put selenium in there. This just has a hydrogen, and this is proline. It has a ring. Now, these side chains in amino acids dictate what their chemical properties are. These are all hydrophobic. The ones we looked at are hydrophilic. Here we even have benzene rings. Again, all of these are not soluble in water. All right, what do you do with amino acids? Well, you link them together. This is an amino acid with a methyl for a side chain. This is another amino acid with an alcohol side chain. This is the amino group. This is the carboxylic acid group. We can link these together, and when we do, we will remove a hydrogen and an OH. That gives us water. We have made an amide. This is called a peptide bond. Again, that's a biological term for the functional group amide. We still have the carboxylic acid out here and amine here, so we can do this over again. And we make what's called a peptide. Peptides are amino acids linked together, each of them through an amide bond. If we keep doing this, we get a protein. Each of these are the amide bonds, just like we just made here. And we just keep going over and over and over again until we make our protein. Now, this protein, made up of all these different amino acids, some of these side chains are going to be water soluble, and some are not. As this protein is being made, it folds itself up so that the water soluble groups are on the outside and the water insoluble are on the inside. This is the enzyme lysozyme. This is it folded up. This was the first enzyme to have its 3D structure determined. You'll note that we have these little red coils. Those are helices, alpha helix. The yellow here is called a beta sheet. See this thing here? That's the active site. This binds a carbohydrate chain in this little active site, and it cleaves it. This is what it looks like as you rotate it around. You can see the coils. These are the alpha helices, and here's our sheet. That's a beta helix, actually. Another way to show the helices is using a ribbon. So something like that. And this is what the molecule looks like in 3D. As it comes around, right in here, this is the active site. This is the mouth, if you will, where the stuff binds and then it's cleaved. See all the blue things? Those are positively charged. The oxygens, those are negatively charged. And all the hydrophobics are stuck in the inside. Every protein has a unique structure based on the sequence. Kind of neat. All right, if we're going to talk about biomolecules, we also have to talk about DNA and RNA, right? Basically, they're a whole lot the same. They're based on a molecule of ribose. This is ribose. And what we do out here is attach this to a phosphate and then to a base pair. Ribose has an OH here in carbon 2. Deoxyribose has a hydrogen instead. That's really the only difference. The things that are attached to the ring, we have what are called purines and pyrimidines. These are our two purines, A and G, adenine and guanine. These are the pyrimidines, cytosine and thymine. One more difference in RNA as opposed to DNA. Instead of thymine, we have uracil, where the methyl group is missing. And of course, we have the OH. As these base pairs encounter each other, you'll note we have an oxygen with unshared pairs of electrons and an NH. We can make a hydrogen bond. We have an NH and a nitrogen, also has an unshared pair, another hydrogen bond. Oxygen, another NH, another hydrogen bond. The bases here recognize each other by forming these hydrogen bonds. If we take the long chain and we put it together, you see we have purine, pyrimidine. These all form hydrogen bonds and stabilize this alpha helix. Again, they're all linked with phosphates. Phosphate, of course, is charged. This is water soluble. It's on the outside. And these guys are water insoluble. They're on the inside. This is another model of DNA. Again, you can see the bases all lined up. And again, the phosphates are in the outside here. See all the charges on the outside and all the bases on the inside. One more view. Ball and stick. Again, here's our bases. And here's our phosphate ring on the outside. Any questions? Remarkable. All right, there's one other functional group that we need to talk about, and that's fats. Fatty acids, lipids, phospholipids. This is a cis double bond, isn't it? You've heard of trans fatty acids. Those are bad. Your body cannot eat a trans fatty acid. It only takes cis fatty acids. So the trans simply accumulates somewhere. Again, long chain, acid functional group on the end. If we hook these to an alcohol with 3 OHs, we get the ester functional group. Again, these can all be different. This is the triglyceride. It is also known as fat. One other version, phospholipid, very important. We have linked this to a phosphate and a choline. These are very water soluble. This end of the molecule is not. These can arrange themselves, kind of like a protein does. They put all of the hydrophobics together with these guys sticking out in the water. This makes a membrane. Membranes surround all the cells. Again, it's just very simple. Water is out here, and we're just staying away from the water on the inside. Again, this is the cell wall. Now, the cell wall actually has other stuff in it. It's very important that this be stable, very important. For that, the body uses proteins and everybody's favorite, cholesterol. This is cholesterol. It's hydrophobic, has an OH on one end, and it buries itself inside the bilayer. When it does that, it stabilizes the thing, makes it good and strong. This is a very, very important molecule in your body. Every cell in your body knows how to make this. Now, we all hear about cholesterol for bad reasons. Turns out you can take, because this is a very important molecule in your body, it has to be transported all over. It does this with a transport protein. Okay? But if that transport protein reacts with free radicals, react to things with one electron, we form a messy, ugly plaque. The real devil here is not the cholesterol. It was just going along for the ride. The real devil is the carrier protein that becomes badly oxidized, clumps together, and makes these plaques. Now, here's a story. I was alive in the 50s, sort of. And we had a president, Eisenhower, former general, nice guy, you know, whatever, fooled around, but whatever, I guess. He was in office, had a heart attack. They took him in for surgery. They didn't do open heart surgery in those days, so this was very risky. And they said that his arteries were clogged with fat. They looked like that. His cholesterol was very high. Well, his doctors put him on a diet. He could not eat fat and nothing at all with cholesterol in it. Now, he hated his diet, and he died anyway. But the people in charge really didn't know their biochemistry very well. Okay? And they said, well, he died because of all this cholesterol that he ate. Loved his bacon and eggs. Turns out bacon and eggs aren't bad for you at all. It's the carrier protein, it's the radicals, it's the peroxides that form. Those are the things that are bad. That's why vitamin C is a radical scavenger, whatever. Nonetheless, the people that were in charge said to the entire country and the world, no fat, our low-fat diet came about. And we were supposed to only eat carbohydrates and more carbohydrates. And when we did that, something happened. Everyone started getting fat. This is what we used to look like. And then that happened. The real killer here is that when we eat all of this carbohydrate, we have excess carbohydrate, it's stored, it's converted to fat and stored in case you ever need it. This is the carrier. Believe it or not, all of this is designed to carry 2 carbons called acetyl-CoA. This is the central metabolite in the entire body. The body takes sugar, 6 carbons, breaks it down into CO2 and 2 carbon chunks. From acetyl-CoA, you can make absolutely everything. Everything you eat is converted to acetyl-CoA. Central. But they do this at different rates. If we eat simple sugars, very quickly acetyl-CoA. Fats and oils are slow. Protein are the slowest. You eat protein, it just sits there, very, very slowly converted to acetyl-CoA. This is important because if we have simple sugars, we build up this level of acetyl-CoA, and what is your body going to do with it? It takes it and converts it to fat. If you eat proteins, the conversion is very slow. So, if you look at chips, which are carbohydrate dipped in fat, and a drink, or a wonderful steak, which is good, which is bad, in this guy, your body will digest the sugars immediately. When it does, all the fat that's in the chips is left over. Your body stores it. If we have a steak, it has fat and protein. Both of those are converted slowly to acetyl-CoA. That's the basis of, well, it's called the Atkins diet, but actually he stole it, nonetheless. The bottom line is, fat does not make you fat. Fat plus carbohydrates make you fat. All right, that's organic chemistry, biochemistry, and some metabolism. Remember, quiz 2 and the assessment has to be done, so do the tutorials. Wednesday, D204 for sample exam review, and sample exam next Monday, right here. Okay? Yeah?
We don't have class one. Do we have class one?
Nope. Thank you for saying that. Wednesday is a very important day. You have to cook a turkey, right? Right. Everyone go cook turkey. Or make ravioli or whatever you do.
Ravioli.
And this is our last chapter, so we can celebrate.
And you won't have lab, so.